The Sierpinski triangle, also called the Sierpinski gasket or the Sierpinski sieve, is a fractal and attractive fixed set with the overall shape of an equilateral triangle, subdivided recursively into smaller equilateral triangles. Originally constructed as a curve, this is one of the basic examples of self-similar sets, that is, it is a mathematically generated pattern that can be reproducible at any magnification or reduction. It is named after the Polish mathematician Wacław Sierpiński but appeared as a decorative pattern many centuries prior to the work of Sierpinski. Constructions: there are many different ways of constructing the Sierpinski triangle. Removing triangles. The Sierpinski triangle may be constructed from an equilateral triangle by repeated removal of triangular subsets. Start with an equilateral triangle. Subdivide it into 4 smaller congruent equilateral triangles and remove the central one. Repeat step 2 with each of the remaining smaller triangles. Each removed triangle is topologically an open set. This process of recursively removing triangles is an example of a finite subdivision rule. Shrinking and duplication the same sequence of shapes, converging to the Sierpinski triangle, can alternatively be generated by the following steps. Start with any triangle in a plane. The canonical Sierpinski triangle uses an equilateral triangle with a base parallel to the horizontal axis. Shrink the triangle to a 1/2 height and a 1/2 width, make 3 copies, and position the 3 shrunken triangles so that each triangle touches the 2 other triangles at a corner. Note the emergence of the central hole, because the 3 shrunken triangles can between them cover only 3/4 of the area of the original. Repeat step 2 with each of the smaller triangles. Note that this infinite process is not dependent upon the starting shape being a triangle. It is just clearer that way. The first few steps starting, for example, from a square also tend towards a Sierpinski triangle. Michael Barnsley used an image of a fish to illustrate this in his paper V-variable fractals and superfractals. The actual fractal is what would be obtained after an infinite number of iterations. More formally, one describes it in terms of functions on closed sets of points. If we let note the dilation by a factor of a 1/2 about a pointer, then the Sierpinski triangle with corners A, B, and C is the fixed set of the transformation UU. This is an attractive fixed set, so that when the operation is applied to any other set repeatedly, the images converge on the Sierpinski triangle. This is what is happening with the triangle above, but any other set would suffice. Chaos game if one takes a point and applies each of the transformations, and to it randomly, the resulting points will be dense in the Sierpinski triangle. So the following algorithm will again generate arbitrarily close approximations to it. Start by labeling P1, P2 and P3 as the corners of the Sierpinski triangle, and a random point V1. Set Vn plus 1 equals a 1/2, where Rn is a random number 1, 2 or 3. Draw the points V1 to var. If the first point V1 was a point on the Sierpinski triangle, then all the points Vn lie on the Sierpinski triangle. If the first point V1 to lie within the perimeter of the triangle is not a point on the Sierpinski triangle, none of the points Vn will lie on the Sierpinski triangle, however they will converge on the triangle. If V1 is outside the triangle, the only way Vn will land on the actual triangle, is if Vn is on what would be part of the triangle, if the triangle was infinitely large. Or more simply, take 3 points in a plane to form a triangle, you need not draw it. Randomly select any point inside the triangle and consider that your current position. Randomly select any one of the 3 vertex points. Move half the distance from your current position to the selected vertex. Plot the current position. Repeat from step 3. Note, this method is also called the chaos game, and is an example of an iterated function system. You can start from any point outside or inside the triangle, and it would eventually form the Sierpinski gasket with a few leftover points. It is interesting to do this with pencil and paper. A brief outline is formed after placing approximately 100 points, and detail begins to appear after a few hundred. Arrowhead curve equals. Another construction for the Sierpinski triangle shows that it can be constructed as a curve in the plane. It is formed by a process of repeated modification of simpler curves, analogous to the construction of the Koch snowflake. Start with a single line segment in the plane, repeatedly replace each line segment of the curve with 3 shorter segments, forming 120-degree angles at each junction between 2 consecutive segments, with the first and last segments of the curve either parallel to the original line segment or forming a 60-degree angle with it. The resulting fractal curve is called the Sierpinski arrowhead curve, and its limiting shape is the Sierpinski triangle. Cellular automata equals. The Sierpinski triangle also appears in certain cellular automata, including those relating to Conway's game of life. For instance, the lifelike cellular automaton B1 per second 12 when applied to a single cell will generate 4 approximations of the Sierpinski triangle. The time-space diagram of a replicator pattern in a cellular automaton also often resembles a Sierpinski triangle. Pascal's triangle equals. If one takes Pascal's triangle with 2 n rows and colors the even numbers white, and the odd numbers black, the result is an approximation to the Sierpinski triangle. More precisely, the limit as n approaches infinity of this parity-colored 2 n row Pascal triangle is the Sierpinski triangle. Towers of Hanoi equals. The Towers of Hanoi puzzle involves moving disks of different sizes between 3 pegs, maintaining the property that no disk is ever placed on top of a smaller disk. The states of an n-disk puzzle, and the allowable moves from one state to another, form an undirected graph that can be represented geometrically as the intersection graph of the set of triangles remaining after the nth step in the construction of the Sierpinski triangle. Thus, in the limit as n goes to infinity, this sequence of graphs can be interpreted as a discrete analog of the Sierpinski triangle. Properties: for integer number of dimensions d, when doubling a side of an object, 2d copies of it are created, that is 2 copies for one-dimensional object, 4 copies for two-dimensional object and 8 copies for three-dimensional object. For Sierpinski triangle, doubling its side creates 3 copies of itself. Thus Sierpinski triangle has housed of dimension log 3/log 2, a permil 1.585, which follows from solving 2d equals 3 for d. The area of a Sierpinski triangle is 0. The area remaining after each iteration is clearly 3/4 of the area from the previous iteration, and an infinite number of iterations results in 0. The points of a Sierpinski triangle have a simple characterization in barycentric coordinates. If a point has coordinates, expressed as binary numbers, then the point is in Sierpinski's triangle if and only if e plus phi plus v equals 1 for all I. Generalization to other moduli. A generalization of the Sierpinski triangle can also be generated using Pascal's triangle if a different modulo is used. Iteration n can be generated by taking a Pascal's triangle with Pn rows and coloring numbers by their value for x mod p. As n approaches infinity, a fractal is generated. The same fractal can be achieved by dividing a triangle into a tessellation of p2 similar triangles and removing the triangles that are upside down from the original, then iterating this step with each smaller triangle. Conversely, the fractal can also be generated by beginning with a triangle and duplicating it and arranging n plus 1 closing round bracket over 2 of the new figures in the same orientation into a larger similar triangle with the vertices of the previous figures touching, then iterating that step. Analogues in higher dimensions. The Sierpinski tetrahedron or tetrix is the three-dimensional analog of the Sierpinski triangle, formed by repeatedly shrinking a regular tetrahedron to 1/2 its original height, putting together 4 copies of this tetrahedron with corners touching, and then repeating the process. This can also be done with a square pyramid and 5 copies instead. A tetrix constructed from an initial tetrahedron of side length L has the property that the total surface area remains constant with each iteration. The initial surface area of the tetrahedron of side length L is. At the next iteration, the side length is halved. And there are 4 such smaller tetrahedra. Therefore, the total surface area after the first iteration is. This remains the case after each iteration. though the surface area of each subsequent tetrahedron is 1/4 that of the tetrahedron in the previous iteration, there are 4 times as many, thus maintaining a constant total surface area. The total enclosed volume, however, is geometrically decreasing with each iteration and asymptotically approaches 0 as the number of iterations increases. In fact, it can be shown that, while having fixed area, it has no three-dimensional character. The Hausdorff dimension of such a construction is which agrees with the finite area of the figure. History: Wacław Sierpiński described the Sierpinski triangle in 1915. However, similar patterns appear already in the 13th century cosmati mosaics in the Cathedral of Hanoi, Italy, and other places of central Italy, for carpets in many places such as the nave of the Roman Basilica of Santa Maria in Cosmedin, and for isolated triangles positioned in roti in several churches and basilicas. In the case of the isolated triangle, it is interesting to notice that the iteration is at least of 3 levels. See also, Apollonian gasket, a set of mutually tangent circles with the same combinatorial structure as the Sierpinski triangle, list of fractals by Hausdorff dimension, Sierpinski carpet, another fractal named after Sierpinski and formed by repeatedly removing squares from a larger square. References: Sierpinski gasket by Trema removal, Michael Barnsley. Al. V. Variable fractals and superfractals CS1 maintenance, explicit use of Al. Feldman, David P., 17.4 The Chaos Game, Chaos and Fractals, An Elementary Introduction, Oxford University Press, pages 178-180, ISBN 9780199566440. Prusinkiewicz, P., Graphical Applications of Lahr Systems, Proceedings of Graphics Interface 86/Vision Interface 86, pages 247-253. Rumpf, Thomas, Conway's Game of Life Accelerated with OpenCL, Proceedings of the 11th International Conference on Membrane Computing, pages 459-462. Bilotta, Eleonora. Pantano, Pietro, Emergent Patterning Phenomena in 2D Cellular Automata, Artificial Life 11, 339-362, doi, 10.1162/106454605440717. Stewart, Ian, How to Cut a Cake, and Other Mathematical Conundrums, Oxford University Press, pages 145, ISBN 9780191500718. Romick, Dan, Shortest Paths in the Tower of Hanoi Graph and Finite Automata, Siam Journal on Discrete Mathematics 20, 610-62, AR Ziv, Math. CO/03101009, doi, 10.1137/0506286660, Mr. 2272218. Faulkner, Kenneth. Fractal Geometry, Mathematical Foundations and Applications. Chichester, John Wiley. Pages 120. ISBN 0-471-92287-0. ZBL 0689.28003. Helmberg, Gilbert, Getting Acquainted with Fractals, Walter de Guita, pages 41, ISBN 9783110,190,922. http www.cutthenot.org. Sierpinski SHTML, Shannon and Bardzell, Kathleen and Michael, Patterns in Pascal's Triangle, with a Twist, First Twist, What is it? More.org, retrieved March 29, 2015, Wolfram, Stephen, A New Kind of Science, Wolfram Media, pages 43, 873, Geometric Floor Mosaic, Nave of Santa Maria in Cosmedin, Forum Boreum, Rome, September 5, 2011, FLICKR, Conversano, Elisa. Tedeschini Lally, Laura, Sierpinski Triangles in Stone on Medieval Floors in Rome, Applimat Journal of Applied Mathematics 4, 114, 122. External links: Haswinkel, Michiel, ed., Sierpinski gasket, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4, Weierstein, Eric W., Sierpinski Sieve, MathWorld. Paul W. K. Rothemund, Nick Papadakis, and Eric Winfrey, Algorithmic Self-Assembly of DNA Sierpinski Triangles, PLOS Biology, Volume 2, Issue 12, 2004. Sierpinski gasket by Trema removal at Cut the Knot, Sierpinski gasket and Tower of Hanoi at Cut the Knot, 3D printed Stage 5 Sierpinski Tetrahedron.